Welcome back, everyone. We are excited to continue our journey together, building neural networks from scratch in the Rust programming language. Today, in part 2 of our series, we will be implementing the algorithm to calculate the gradient for each node in the computation graph. Just to refresh your memory, in part 1, we defined the value data structure and implemented common mathematical operations that are used in neural networks, such as addition, multiplication, subtraction, and tanh. They're implemented either as the methods of value data structure or the traits from the standard library. For today's session, here is the agenda. We will first start with a demo in which I will show you the final result of today's session. Then we will dive into the introduction to gradients in the neural networks. We will discuss the concept of topological sort and its application in neural networks. And finally, I will walk you through the implementation. In the implementation, we will do the topological sort, then we will visualize the computation graph, and finally calculate the gradient. Let's kick things off with the demo. In this demonstration, we are going to firstly construct a computation graph. We defined a bunch of variables and combine them using various mathematical operations. Ultimately, we receive V6, our final output. Then V6 is passed to the function calculateGrad. This function is responsible for updating the gradient of each node in the computation graph. We also pass V6 to the function visComputationGraph, which generates a PNG file. This graphical view lays out the structure of our computation graph along with the inner values of each node. Here is what happens if we run this code. A PNG file will be created, which when opened provides a clear and visual representation of the structure of our computation graph, and also the inner values of each node. So stay tuned as we proceed further to break down the underlying concepts presented in this demonstration, providing a more in-depth understanding of the implementation of gradients in neural networks. Now that we have experienced hands-on, let's delve into the related theories, starting with the gradient. In mathematics, gradient is the slope of a function. It represents the direction and the magnitude of steepest ascent. In the field of neural networks, the key concern is the value of the loss function. When we try to optimize the neural networks, the ultimate object is to minimize the loss function. And because the gradient tells us the direction and the magnitude of the steepest ascent, it can guide us in adjusting the weights and the biases for optimal decrease of the loss function. To calculate the gradient using the computation graph, we need to apply the chain rule. If a variable z depends on variable y, which itself depends on variable x, then z depends on x as well, via the intermediate variable y. In this case, the chain rule is expressed as dz over dx is equal to dz over dy multiplied by dy over dx. So here is an example to illustrate this chain rule. If a car travels twice as fast as a bicycle, and the bicycle is 4 times as fast as a walking man, then the car travels 2 times 4 equal to 8 times as fast as the man. All these pictures and codes are from the Wikipedia. So let's do a little exercise to help us understand the chain rule. Here is a very simple computation graph with 5 variables. V1 times V2 gives V3, and V3 plus V4 gives the final loss function value. So how are we going to calculate the gradient with respect to V1? Here, V3 is the intermediate variable. So dl over dv1 is equal to dl over dv3 times dv3 over dv1. By using some high school or undergraduate school mathematics, we know that dl over dv3 is equal to 1, and because v3 is the product of v1 times v2, so dv3 over dv1 is equal to the value of v2, which is 2. So ultimately, dl over dv1 is equal to 1 times 2 equal to 2. Let's pause for a while to make sure that we understand how to apply in the chain rule to calculate the gradient of a certain node. So here is the key question. Apparently, in order to apply the chain rule, we need to follow the order of dependency. But how are we going to get this order programmatically? So naturally, we need to introduce the topological sort. In computer science, a topological sort or topological ordering of a directed graph is a linear ordering of its vertices, such that for every directed edge uv from vertex u to vertex v, u comes before v in the ordering. To apply that in the neural networks, as we already learned that neural networks is a directed graph, and we use various math operations to build a graph. For example, A plus B produces C. And here we construct two edges. C depends on A, and C also depends on B. In the topological ordering, C comes before A, and C also comes before B. So I think we have been equipped with sufficient mathematics and computer science. Now let's turn to implementation. First off, we are going to implement the topological order function. It accepts one parameter, root, which is the output value of a computation graph. The function will return a list of nodes in the topological order. We begin by defining two mutable variables. The first is order. It is a linked list where we will add the nodes in topological order. The second is visited. It is a hash set that will help us in keeping track of the nodes that have been visited. I've chosen to calculate the topological ordering in a recursive fashion. Here is why. If we already know the topological ordering of a node's children, we can simply add this node to the front of the ordering list. This top-down approach is quite intuitive and succinct. However, there are also some risks involved. This approach particularly has some drawbacks when dealing with very large computation graphs. Specifically, every recursive call adds a layer to the call stack. If the computation graph is exceedingly large, this results in making an extremely large number of recursive calls. This, in turn, might cause a stack overflow error because of exceeding the stack limit. However, for the purpose of our educational code and understanding the fundamental concepts, we accept this risk. In a production environment, we would optimize this to handle larger data structures without running the risk of stack overflow. Okay, now let's turn our attention to the implementation of this recursive function. The function requires a reference to a value, a mutable reference to a hash set visited, and a mutable reference to a linked list order. If the value's ID is not contained within our visited set, we can then insert this value's ID into visited. The purpose of visited is to keep track of the nodes that have been visited during our depth-first traversal, ensuring that we don't visit any node more than once. Next, we examine for the operation associated with the current value, which is value.op. If the operation is none, we do nothing because there are no child nodes. If it is add, or multiplication, or subtraction, we recursively call depth-first function twice, as both these operations have two child nodes represented by v1 and v2. In case of tanh_edge, we call depth-first once, as the tanh_edge operation has only one argument, v1. Note that the depth-first nature of this function allows us to process all child nodes before processing the parent nodes, aligning itself perfectly to the requirements of topological ordering in this case. Having defined the depth-first function, we invoke it on the root value, together with the empty visited and empty ordering. After this function finishes, we are sure that it has visited all the nodes in the graph, and then we simply return the order. Next, let's walk through the implementation of the function Computation graph. It uses the graph create to generate a visualization of a computation graph. The function takes two parameters. The value is a reference to the value object, which is basically the output of the computation graph. The graph is a mutable reference to the graph object. We will mutate it by adding the nodes and edges. The function first calls the topological order function to obtain a topological ordering of the value object in the computation graph. This ordering ensures that the nodes are processed in a way that respects the dependencies between them. Then, we iterate over the value objects in the topological order. For each value object, it performs the following steps. First, it adds a newly created node to the graph object using the add statement method. The ID of the node is equal to the ID of the value object, and we will label this node with the inner values of the value object, such as the data, the current gradient, and the math operation. The function then adds edges to the graph object to represent the dependencies between the current value object and its parent nodes. It does this by iterating over the parent nodes and creating a new edge using the edge macro, which are then added to the graph object using the add statement method. The specific edges added depend on the operation type of the current value object. For addition, multiplication, and subtraction, the function adds edges from the two parent nodes. For operation tanh_edge, the function adds an edge from the single parent node. For non-operation, no edges are added. By following this process, the function builds up a complete representation of the computation graph in the graph object, which can then be used to generate a visual representation of the graph using the graph create. So here comes the focus of today's session. to calculate the gradient with respect to each node in the computation graph. So we define this function calculate grad. It takes one parameter root, which is ultimate output value of the computation graph. Because each value has its op field, which contains the operand values. That means we can walk through the whole graph by following this link, starting from the root. In the implementation of calculate grad, the gradient of the root node is set to be 1.0. This is the starting point for backpropagation. Then we invoke the function topological order on root, which returns a list of the value object in the topological ordering. This ordering is necessary to ensure that gradients are computed in the correct sequence from the output node back towards the input nodes. Then we iterate each value in the topologically sorted list. For each value, it performs the following steps based on the type of the operation associated with value. If the operation is none, it means V has no operand nodes and it is a leaf node in the computation graph. We don't need to do anything. If operand is add, that means V is the addition of its two operand nodes. Let's say V1 and V2. So V equal to V1 plus V2. Here we want to apply the chain rule. So V is the intermediate variable between the loss value and V1 and V2. For example, if we want to calculate the gradient on V1, then dl over dv1 is equal to dl over dv multiplied by dv over dv1. dl over dv is exactly the gradient of v, which should have already been calculated because we are following the topological order here. For dv over dv1, using some high school or undergraduate math, we know that it is equal to 1. Then dl over dv1 is equal to the gradient of v multiplied by 1. In the case of multivariate derivatives, we want to add this term to the current gradient of v1. We perform the same operation to v2's gradient as well. For the case of multiplication and subtraction, it is very similar to how we deal with addition. The only difference is how we calculate the derivative of the intermediate variable with respect to its operand variable. For example, in the case of multiplication, v is equal to v1 multiplied by v2. Therefore, dv over dv1 is equal to the value of v2, and dv over dv2 is equal to the value of v1. That's why we need to use get data of v2 here, multiply the gradient of v as the term to update the gradient of v1. In the case of subtraction, dv over dv1 is 1, and dv over dv2 is minus 1. So the term is actually v's gradient multiplied by 1 and v's gradient multiplied by minus 1. For the hyperbolic tangent function, the math is a little bit more complicated to calculate the local gradient. You can check the Wikipedia or other places for how this local gradient is calculated. Still, we can apply the chain rule. Gradient to update is still equal to the gradient of the parent node multiplied by the local gradient. Alright, so we have completed the implementation of the three main functions to get the topological order of the computation graph, to visualize it, and to calculate the gradient. Now let's test it out. In this unit test, I use the 6 variables to construct a computation graph. The output of the computation graph is V6. Then I invoke the calculate gradient on V6, which it will iterate all the nodes in the computation graph and try to update their gradient. Then I create a new graph we call the V's computation graph on the output node as well as the graph to update. When this function returns, the graph is added with the nodes and edges. We call some utility function to output the final PNG file. I've already run the unit test, and let's see the output. So this is the output PNG file. At the bottom is output of the computation graph, V6, and it is the tangent edge of its operand node. In each node, it correctly shows the data, gradient, as well as the operand. For exercise, you may manually check if the gradient of each node is calculated correctly or not. So this concludes our today's session. To summarize, today we introduced the concept of gradient and its usage in neural networks. Then we implemented several key functions, such as how to calculate the topological order given a computation graph, how to visualize it using the graph-viz crate, and finally how to calculate the gradient of each node. Next session will be the last, in which we will implement a multi-layer perceptron API and try to use it to train a neural network. See you next time.